Okay, I think we might, as that number slowly starts to grow over the next couple of minutes, I'll just work us into today's session. So welcome everybody. My name's Chris Thompson and I'm from the School of Chemistry and I'm an Associate Professor and a Physical Chemist by trade. And I'm also the Associate Dean Education working in the faculty office. But today's absolutely not about me. You're going to hear from one of our amazing professors. And the title of today's webinar is It's a Machine's World, How Automation Changes Chemical Synthesis. But before we get into today's session, I would just like to make an acknowledgement of country. I wish to acknowledge the people of the Kulin Nations on whose land we are presenting from today. I pay my respects to their elders, past and present. So welcome alumni and stakeholders. Thanks everyone for joining us today, and I'm noticing that the number is still slowly climbing up in the bottom, so we'll probably start to see a few more people joining us over the next few minutes. Look, the Faculty of Science have more than 40,000 science alumni, and we're really proud of our students and alumni. We want to stay connected with you, share the latest research, news from the world of the faculty, and that's everything in terms of research and education. Even though we can't meet in person at the moment, we still want to stay connected. And so this year we've been trying to do that in a virtual way. And so today is an example of how we're trying to stay connected and share our research and ideas that are coming out of the school and how our researchers are connecting with the way science is moving in a modern world. Just a quick bit of housekeeping before we get into today's session. So the Q&A is going to happen after the presentation. Here's how it's going to work. To ask a question, please use the Q&A function in the toolbar at the bottom of your screen. Remember to upvote your favourite questions when you see them coming through from other people. And our alumni manager, Claire O'Grady, is going to be in the background monitoring those questions and chats. And then she's going to push those questions through to me when we get to the question. So we'll be about 35 minutes into the session, 40 minutes into the session. And when our speaker has finished, we'll move on to those questions. So that's how it's going to work. So please, if you've got any great questions, open up the chat window and ask away. Just a quick update on the School of Chemistry. Even though it's been a really strange year, we know it's been a strange year for everyone, and it's been a very strange year for universities, I can assure you of that. Just recently, the School of Chemistry has been awarded 7 Australian Research Council Discovery Project Awards for the 2021 round, which is absolutely mind-blowing. The success rate for these sorts of things is around 15%. So for us, it's closer to 40%. And it's over $2.5 million that have come into the school for projects that will kick off next year. 2 of our stars of the future have received ARC Future Fellowships this year. That's Vicky Blair and Sasha Simonov. So some great news in what's otherwise been a really challenging year. Just quickly, before we talk about research, I want to tip my hat to our educators who've really bent over backwards to deliver our programs online, with the goalposts constantly shifting. Look, I'm pleased to say our students' performance has continued to be fantastic. And while it's been tough on them, they've also let us know that they understand and appreciate what we've been able to offer them this year. So even though it's been a tough year, we're coming to the end of it and we're really optimistic about next year. Now, it's time for me to introduce our speaker. So Professor Tanya Junkers, who's one of our professors in the school, graduated with a PhD in physical chemistry from Göttingen University. I never know if I pronounced that correctly. I'm sure I don't. You can fix that one up for me, Tanya. From where she moved on to work at the University of New South Wales and the Karlsruhe Institute of Technology. I'm sure I butchered the pronunciation of that one as well, where she was appointed professor at Hasselt University in Belgium. Early in 2018, she moved to Monash University in Melbourne, Australia. Her research focuses on precision polymer synthesis, radical reaction kinetics, machine learning in synthesis, and to a very large extent, continuous flow synthesis of functional materials. Not my area of expertise, so I'm going to hand it over to her to tell you all about it. Over to you, Tanya.
All right, many thanks. I hope you can see my screen. In fact, you pronounced all the German city names pretty well, Chris, so congrats on that. It's indeed not easy. Now, as you mentioned, I'm a physical chemist by training, and over the years, I've become more and more a person to do chemical synthesis, and within the School of Chemistry, I'm often lumped into the organic chemistry crowd, which is okay for me, but you will see actually a lot in my presentation today that my heart is still with physical chemistry. And if you go to this interface of physical chemistry and synthesis of materials, synthesis of polymers, you end up very, very quickly in the realm of chemical engineering or polymer reaction engineering. And that's exactly what we do. But I'll come back to that a little bit later. So, yeah, 2020 has been a truly remarkably weird year. And I think it's a good thing to do at the end of this year to look into the future and to have an idea, okay, how could the future look like? And I think that's something, especially in the chemical sciences, we really have to do, because there have been tremendous changes in the way things are done in the past years, which haven't really reached the chemical realm yet. And it's time for us to acknowledge that, and actually more and more labs around the world do acknowledge that and are starting to implement changes. And a lot of these things I'm going to try to show you the potential about today. It's a topic where we are still in the infancy, really, and where lots of developments will come in the next years. But I'll try to show you a bit where this story will go to and how we might actually be doing chemistry in 10 years from now. And it might not be what you think it is. So let's have a look at this. Long story short, what I'm talking about is automation, or you could also say digitization of chemistry, actually making all the steps that we are used to do in a chemical laboratory available to machines, and slowly but surely give a handover to machines and give us the ability as a chemist to actually do the interesting work, which is the creative part, and not the part where you stand in the lab and you do manually the same thing like shaking your beakers, but give that to a machine. That machine can do that better than we, actually can also do it in a smarter way than we can do it. All right, but before we get there, a little bit back to the past, because it's very important to see where we are coming from to understand the present. And as you see here from this old Charlie Chaplin movie, City Lights, automation is something, or machines are around since actually a long time. So from the start of the industrialization, our whole economies and Western societies had a remarkable transformation from a society where people would handcraft things up to where machines do actually a lot of the work. And that's important to see, because here, this is something that is basically 100 years old now, if not more. But in the chemistry space, well, I'll come back to that. It might be a little bit different than that. And that's important to understand in order to see what the future might bring for us. So one thing in terms of automation, if we go to the Industrial Revolution, a real big milestone is actually this little thing here. That's Tin Lizzie, built 110 years ago by Henry Ford. And this was one of the first cars that was mass produced and actually was made available to the common public. Now, what was it that Henry Ford actually did to make these cars affordable to a broader public, and how was he able to do this? And the invention that he actually made was not so much an invention on the side of the car itself, it was the invention on the side of how the car is produced. So he actually introduced production lines. So rather than having workers working on a car and then moving from car to car, he would have the workers stationary, and the cars and the parts you need to build the car would pass the workers. And in this way, you create a production line, you create this modern way of producing goods. And that just gives you a boost in efficiency, because you can also then specialize your workers. Each worker can do a very specific task really, really well and doesn't have to do all the different tasks all together. And that's, of course, 1908. How is that looking today? If you go to a modern car factory, well, we'll see it's looking like this. So actually, digitization also has taken over. By now, it's not only humans anymore. In some parts, there still are. But in many parts, actually now in the assembly, we see here the production belt where the cars are coming through. But nowadays, it's robots who do that. So we see robots play a big role in the modern way of increasing efficiency. All right, with that knowledge, I guess, no one's surprised if I tell you, well, there have been so tremendous changes over the last 100 years in what we do, and especially computers have changed a lot. But how is that in chemistry? And for sure, I mean, everybody who has a bit of background in chemistry will know, well, there have been huge developments in quantum chemistry and the way of calculations we can do, spectroscopy, computing there. There have been a lot of revolutionary introductions into the chemical space. But this is all in the periphery of chemistry. This is all in maybe in designing molecules or materials. This is in characterizing molecules and materials, but not so much in making them. And to see how we make chemicals, again, as I said, you have to look to the past to understand the present. You can go to some old laboratories and actually have a look what actually happened at that time when chemistry was born. And a really nice place to see that is the labs of Justus Liebig in Gießen in Germany. And this is actually the old chemistry building at Gießen University, which is today Justus Liebig's university. It's actually got the name of him. And this is one of the places where the early chemistry was done. And the beautiful thing with that is, and if you ever come to Europe, if you ever come close to Frankfurt Airport, it's about a 1-hour drive from there. I can highly recommend going there, because this place is still around, and the old lecture hall of Liebig is still there, and his old laboratories actually are still there. And it's today a museum that you can actually have a look at. Now, if you go in there, you will see the first laboratories he had. They looked something like this, and this is truly what we would call alchemy. So you still see here an oven with wood fire, and you would place pots on top, and well, that looks pretty dangerous. And apparently, I was told back then, back in the days, actually studying chemistry was really dangerous. Actually, students did die quite frequently during their education in these labs because things would explode. Now, but this is only the old part of the labs. Actually, Liebig actually invented a design for more modern labs. You can also see that in the same building, and that's what it looks like. So this is the modern part from the second half of the 1800s. And we see here actually already fume cupboards, and we see flasks, and we see condensers. I mean, most of you will be familiar with the Liebig condenser that we are using until today. And if you look closer here to a fume cupboard, actually it looks oddly familiar. And if you compare this now to a modern fume hood that we use today, then we see there's really not much difference. So what did we introduce today? Today, okay, we got a gas line, we got some safety installations, of course, because we don't want our students to die. And yeah, you got electricity. But basically, the whole concept is still the same. And this is very important to understand here. Actually, Liebig was a person to introduce a lot of technology, a lot of techniques into labs that we are still using today, that we are still teaching today to our students. And essentially, nothing has changed. We might have a little bit better glassware. We might have a little bit better connectors and these things from plastic materials. And of course, we got magnetic stirrers to automatically stir solutions. But essentially, we are doing what people have done 150 years ago. Chemistry is incredibly conservative. So we haven't changed our way. We use computers in the periphery, but we do not use them at the chemistry itself. If you go back to the example of a car manufacturer, we are not Henry Ford. We are actually before Henry Ford in what we do in chemistry. And it's time to change that. It's time to actually take the next step. So looking at chemistry again, so yeah, being in Melbourne, coffee is a great example or a great metaphor to compare this. So this is what we do. We do handcrafted chemical synthesis and production. So we have our chemical reactors, and actually brewing a drip coffee here is nothing else than a simple chemical extraction process. And we do this. And we believe that we as chemists are educated and we have the experience and we can make the best thing. So as like a good barista, we think that we can by hand make the best chemical compound. We will make the most efficient synthesis. We will make a beautiful molecule with a high purity, and we are just best in doing that. And this stems from, just again, to stay in this metaphor, from the idea that a machine could never have the intuition that we have. The machine could never have this really sensitive view to react on a reaction and to work on it. And we often would think that if we had a machine, we would get something like this. So sure, yeah, they are coffee machines, but this coffee is obviously terrible. And people think, well, for chemistry, it's probably the same. It's probably also just going to give us terrible chemistry if you try to give that to a machine. But then you also have coffee machines like that, where we would all probably agree, it's maybe not the best coffee in the world, but it's a pretty decent one. So it's something you can actually already work with. So if you stay in this metaphor, you would say, well, actually building a machine that is able to do the job that we think that as humans, as chemists, we would normally be best at, might actually be possible. And this is where it gets really interesting. So there's a pretty recent study from Lee Cronin's lab. And Lee Cronin in Glasgow in Scotland did a fairly simple experiment. And I love this. I mean, the chemistry itself here is actually not that important. It's a crystallization that was carried out. But basically what it did was, there was this reaction where there was literature for, and you can see there's actually an initial set of data. So different people have done these reactions with different conditions and different outcomes. So he gave this reaction to his own PhD students and said, okay, look, use your intuition, use your intellect, read these data sets and start experimenting. And I want to see how good are you? How well are you in reproducing that and optimizing this? And at the same time, he also took a computer, used basic machine learning algorithms and told the computer, learn from this data and see what you get. And interestingly, this is the outcome. If we look at just humans in green here, actually the performance was only slightly better than random data. So if random just means we pick just random conditions without thinking about them. So actually the human intuition has been shown here to be really bad. And the algorithm in red actually performed a lot better. So computers actually are more than capable in outperforming humans. So going back to the coffee, actually the coffee machine can make a better coffee than a barista. And is that the end of the world? Is that the end of chemistry? And luckily it's not, because he also formed a team between his PhD students and the machine learning algorithm, actually allowing the students to interact with the algorithm and to correct it where it went wrong. And actually that team was the best performance. So actually a match of chemists with a computer is actually the best thing you can do. And that's actually what I'm also myself personally believe in. And that's actually where I think what we should be doing. We should use computers in the design and in the execution of our experiments. And a very nice example was also published last year by the team of Klaus Jensen at MIT. They actually built this little robot here, but actually is able to carry out synthesis, and it does even more than that, actually can enter a target molecule. Then the software will actually go to the Reacsys database and actually look at all the reactions that are out there. Basically it screens all the published reactions itself. It compares this with commercially available compounds that you can buy, and it will propose itself a complete synthesis route to this molecule and then start via the use of robotics in making it. Of course, there are still some limitations, but you see clearly where this is going to. And actually, with that example, I could basically end my talk because this is really what the future will look like. But of course, I will not end it here because I want to show you a bit what we are doing at Monash University. So a very interesting part of the robot that Klaus Jensen was building or has built is actually flow chemistry. So if you look at the previous picture, you would see there's no flask around. And that's a very important evolution step. So first of all, we have to get rid of flasks. Why? Because flasks are inherently flexible in use, but they are not very capable when it comes to automation. Because flasks have to be filled, they have to be emptied, they have to be cleaned. This is all not working really, really well. Actually, what works a lot better is so-called flow chemistry. So instead of mixing components together in a flask and then stirring, what we do is we actually take two different channels here. This is shown here in on a glass chip where two different dyes are coming together. They start to mix. You see this here in the color change. So that's the mixing of the two components here. And then they travel with a certain pump speed along the reactor axis. And over this time, a reaction happens, which again is something we see here in the color change. So here from purple to green, a chemical reaction is happening. And we just can collect at the end of the reactor what we're doing or what we've made. And the principal difference is, first of all, this is a continuous process. It's a process we can control a lot better than a flask. And very importantly, the reaction time in such a reactor is given by the flow rate. So for a flask, we mix things together and we look at our watch and we see, oh, we have to wait for half an hour. We're not doing this in a flow reactor. In a flow reactor, we will set the flow rate in comparison to the volume of the reactor, and this will give us the reaction time. So if I pump with 0.1 milliliters and I have a 1 milliliter reactor, my reaction time will be 10 minutes. And of course, this here looks complicated, so that's why I have this little video here from our lab, just showing how these reactors look like. Actually, they're fairly simple. It's a syringe you have here on this side, which is powered by a syringe pump, like you would also find in a hospital. It's actually the same brands. And then it goes here into tubing, and the tubing can put to temperature via oil baths, and just at the exit, we're collecting this. So this is not more complicated than what you would normally see in a chemistry laboratory. It's a little bit different thinking, but it's perfectly possible to do this in every lab. All right, so what are the advantages of flow chemistry? Why would you want to do that? So I mentioned better precision, and we can see this actually here when we go into the temperature profile of a reactor. So batch is standing here for a flask, for a conventional reactor, and microreactor stands here for the flow reactor. And we see actually the temperature profile, and this is just based in physical chemistry, so you just have to want to believe me that this is true, but it is true, so it has been proven over and over again. In a microreactor, we have a much more narrow temperature profile than in the batch reactor. So on average, both will have the same temperature, let's say 100 degrees, but the microreactor is much more precise. And this has a huge advantage for us. And that is something we can see when we convert this temperature profile into an energy profile and go on an energy axis. And we look at the conversion of compound A to compound B. So if you have here our starting material and here our products, so typically we would need to go through our excited state, our transition state here. We have to overcome the activation energy to get to our product side. And we see here, if you look at this diagram, this reaction is going to work in a flow reactor and in a flask. Both will actually provide enough energy to do that. But let's assume we also have a side reaction. A side reaction where A also reacts to C, and C is something we do not want to have. And this has a higher activation barrier. Then we see actually this reaction is going to happen still in the flask. So if you look here on the y-axis, this is still within the temperature profile of our flask, but it's not within the profile of our flow reactor. So actually, this here is something that only happens in a batch, but not in a flow process. And this gives us actually the point where we can see that a flow reactor is not only better in controlling and handling it also gives us a better result for our chemistry. So we can actually improve the chemistry by going to these flow reactors. And there's just a myriad of different opportunities, and people actually are more and more adopting this. So actually, if you go to industry, this is actually an old hat. Industry is doing flow chemistry already since decades. And in academic labs and research and development, this is actually also increasing more and more. So if I look now just at Monash chemistry, I'm aware of 2 research groups already doing flow chemistry and 2 more who are actually actively starting to build capacity in that space and actually start using it. And I'm pretty sure that pretty much every synthesis lab in the future will actually use flow chemistry as an alternative to flask chemistry. It will never fully replace flasks, but it will become an equal thing to do in our chemistry lab. Now, very quickly, for my own research group, to introduce what we are doing in order to understand data that I will show later on. We are called the Polymer Reaction Design Group. So what we do is we make polymers in hopefully as efficient and simple ways as possible. And if you talk about polymers, then we talk about plastic materials. So are we making plastic bags? And the answer is, well, not really. I mean, we can, but typically we work on the things that you see here on the right. So if you look at a polymer, actually you can talk about functionality, chemical functionality of polymer chains. You can talk about topology, making a linear polymer, star polymers, brush polymers, cyclic polymers, networks, whatever you like. And you can start playing with the composition of having homopolymers, random copolymers, block copolymers, and so on and so forth. And what we want to do is we want to actually control every aspect of a polymer. So we want to make polymers with very specific functionality, very specific topology, and very specific composition, which means we are making polymers which are extremely high in performance and actually getting closer and closer to nature. So actually in some parts, we really make biomimetic materials where we try to mimic the function of peptides, for example, in a synthetic polymer. But that's just very important to understand later on what we're going to do. So actually later you will see functionality and composition is something that we are really working on. And we are working a lot on distribution and seeing how these polymers are distributed, because each polymer, when we make it synthetically, is inherently irregular. So we are not as good as nature. Nature can make something like DNA in a protein with a very specific molecular weight. We as chemists cannot. We make a polymer and we always get a mixture. So I can make a certain polymer here with a certain functionality, which is linear, but I will not just make one chain of a certain molecular weight. I will actually make all the chains of different molecular weights. And I will just get an average value. And that's what you will later see in a lot of distribution files that I'm showing to you. So why is flow chemistry now specifically interesting for polymer chemistry? And that is because in polymer chemistry, we're doing the same reaction over and over again. So the difference between a plastic bag and a carrier for cancer therapy and drug delivery is actually really only how much we can increase the precision of our synthesis. So you see here the low range. If we have little control, we will be at classical plastics or glues. We can go to high performance materials if we increase it a little bit. And if you go towards nature's materials, biomedicals or science, well, then we need a very, very high precision. And flow chemistry is just ideal. Just giving here a quick example. So what can flow chemistry do for us? This is something I particularly like. So if you look at isoprene as a monomer, so that's our caoutchouc, so that's what your tires actually are made of in your car, and you want to do a polymerization of that in a radical polymerization, which is the process used in industry to produce the bulk of all materials, of all plastic materials. It will typically take about 72 days to do that. Here we see the typical distributions you would get from such a reaction. Now, I'm not going into the details of the chemistry here, just for you to show that if you use a flow reactor, and in this case, we actually combine it with the action of light, of UV light, actually we can bring this reaction down from 72 hours to 1 hour. So we can get massive efficiency gains just by switching to a flow process. So that's just as an example what powerful technique flow chemistry is. It's not just something where you change your mode of operation, it's not just pure engineering. It is actually giving us access to very new chemistry. And if we look then further for more complicated things, so I was mentioning peptides. In peptides, you want to bring different chemical functionalities into an order. We can do the same thing now in our polymers. So we can actually make what we call a blockopolymer, where you put different blocks of polymers in an order and actually in this way start to have a sequence of chemical functionalities. And again, we can compare a batch process, which you see here, with a flow process up here. And actually the flow process is much more efficient than a batch process. Again, no details in chemistry, just showing you some numbers here. This PDI, this dispersity index value is basically an indicator for quality. The lower, the better. And we see here for 5 functionalities in series, we have still a fairly low number, while in a batch process already at 3 functionalities, we have a very high number. So we see actually using flow makes things a lot better. Now, knowing it makes it better, actually I want to really talk about automation, not so much about flow chemistry as such. How do you automate this? And this is a very nice example that we built up, where we wanted to make these polymers here, where we put a sequence of monomers after each other. And in the last slide, I was showing examples which we made by hand. Each polymer was collected and then further reacted. But we also wanted to build a machine which does that actually automatically. So you just start feeding one monomer, you have your first reactor, then automatically you feed in the next, you react it, you feed the next, you react it, you feed the next, you react it. And at the end, you just collect your polymer. And you see that such a machine here already, where you have different pumps and different reactors just in series. So actually we can get these complicated polymers in one go, where in principle in the morning, only technician has to turn this on and come back in the evening collecting the materials. Of course, it's not as easy as that, and that is because we still have to optimize our reactions. Optimization is a very, very big part, and I like this little metaphor here again. So assume this is actually a reaction you're doing, and this is just a progress of your reaction, where the height here at the end shows you how much material you've made. And if you do this reaction conventionally, you will be able to record this, and you come to the end point. And then you realize, wow, I should have really gone back in time, and I should have changed something here. If I would have done something differently here, well, I would have come to a better result. And this sounds like science fiction. But it really isn't, because in flow chemistry, we have the advantage that our residence time, as you remember, is given by the flow rate. And the flow rate I can vary in both directions. I can go to higher flows or I can go to lower flows, which means if I go to a higher flow, I can travel back to this specific point here, make a change, and then change the flow rate again. So in a flask, time is linear. In a flow reactor, actually, it isn't. Well, time is, of course, still linear, but we can go back and forth on the reaction axis via the flow rate. And this is not something we can use to actually sweep through reactions. And first of all, we can use this now for detection. So we see here a flow reactor attached to a mass spectrometer. And what we simply do is we start at one flow rate and then we change to another flow rate and just record what's happening in the middle. And then you see something like this. So each peak you see here is actually an individual polymer chain. So we see different chains, a distribution, because you have different length. But now we can actually see the polymer growing. So we can watch this process, because every second we are getting a new spectrum, and we are screening through now actually all the reactions by the combination of flow chemistry and an online detection tool. So we now have a very, very fast feedback for our reactions. And we can use that even further. So mass spectrometry is one, and I'll just show this here quickly. In our labs now we have a system where we combine other detectors. So again, you see here our syringe, which actually feeds our starting material, the monomer. Then it goes into our flow reactor here, where we react. So by varying the flow rate, we can vary the residence time in that reactor. Now everything that comes out is not collected. It goes directly here through a 60 megahertz NMR spectrometer. It comes out here on the top, so we can measure directly all the NMR spectra for our reaction. Then we go to a dilution stage that you see here. We pump in a bit more solvent because we have to get down in the concentration of our material. And then we inject everything here into chromatography via this injector module here. And this will allow us to determine the molecular weight of our polymer automatically. So we do not have to do anything anymore. We can collect all this data in one go. And this allows us now to introduce machine learning. So if we have such a setup, in this case you see it without the NMR, so different pumps here in this case, we have a bit more complex setup, but the same idea, go to the flow reactor, go to chromatography. We can actually use that now to actually automatically read out the results. So we are cutting out the human factor, we are cutting out the person actually doing the analysis and entering this value, because the computer can do this alone. So the computer feeds the result of its reaction back, and we give the control over the pumps to the computer. So the machine learning algorithm we use actually is now able to guide itself. And then we can just merely program in what we want. We can say, I want to have a certain molecular weight of my polymer, and voila, the machine will find it. It will make mistakes in between, and it learns from its mistakes, and it corrects for its mistakes. So we can jump here to different levels and make these different molecular weights in a very, very reproducible manner. We can even increase the accuracy here and go to extremely high precision. So that's something no human chemist can do. If I send any PhD student or an experienced postdoc to the lab, and you would say, I want to have exactly this molecular weight and this accuracy, they would not be able to do this. But the machine actually can. So that's the really nice thing. And we can use that for a lot of different reactions. Again, I'm just jumping through some examples. You will have to believe me that this is actually correct. So here we use that for blocker polymers, again, where you put different chemical functionalities, different blocks attached to each other. And again, we can reach the same accuracy, and we can now make chemistry programmable. We can actually program what we want. We go, press start button, go have a coffee, come back, and the product is there. It's made for us, and it's made better than we ever could. We can also give it to process control, so we can also make sure that the reactor keeps it stable over an extended period of time, so we can actually go to production. So that's the question we typically get. If you have these really small reactors of 1 milliliter, does it mean you can only make milligrams? And the answer is no. Actually, in a fairly high flow rate in a 1 mil reactor over a day, we can easily make hundreds of grams of material, which for these polymers we are talking about here are actually already values of tens of thousands of dollars. And this is just examples now for other detections. So we can actually now also feature in the NMR that I've showed you, which allows us to measure the progress of the reaction to get more efficient on that axis as well. And just different examples now that we can use this now for another level of control that we can introduce, but also for very rapid screening. So we can now do kinetic screening on these reactions, where in my own PhD, I would have spent a month or two in screening one reaction like this here. We can now do basically in one afternoon. So we get the data much quicker and much more precise. And yeah, this is just another example where we use these algorithms then in machine learning to actually match our polymers, and again make the same polymer over and over and over again, starting from different conditions and still matching all the time the same distribution. Again, something a human could not do as easily. So we really see the potential here. The machine can go a lot further than our human workers could. And the machine learning is just the beginning, where we actually are able to program what we want. So actually, we have lots more plans for the future to go into even more complex materials. And we can use this now to actually make really new things. So we can also build the system in a way that we start collecting, and we can actually make mixtures of different polymers. Just something I want to show quite quickly. So if you want to make a distribution here where we tune the broadness of that distribution, it's typically not easy. So that we don't have any chemicals tools to do that. And we can actually now reach that by programming our computer and say, I need these different polymers here. So that's a simulation we did before. We see, okay, I need to make these different polymers and mix them together in precise quantities. and then I will get this desired product that I want. Again, by hand, almost impossible, but the machine reaches that accuracy and can do that actually quite well. So we can now make all these different polymers, and we can actually now start making that and studying the properties of these materials, which by classical methods would not be available. Again, just jumping over this quite quickly because yeah, I don't want to go too much into detail into distribution shapes. And just showing you how far we can go, we can actually go as far as to make whatever we want. So we can now start creating what we call the Uluru shape distributions, or the Batman distribution, which we are quite fond of. So we can actually start making that. So we can actually go really away from the classical chemistry and start making completely artificial things in these methodologies that yeah, you could otherwise never do. And of course, this serves a purpose. So if you look at Batman distributions, why would you want that? Well, Batman is maybe not the best example, but changing the broadness is something that we can use, for example, to play them in self-assembly. So lots of these polymers that we are making are used for self-assembly, for nanotechnology. And we can now use these features to control the self-assembly. So we can actually see that, you know, somehow the assembly of nanoparticles changes depending on the distribution that we enter in here. And that's again just at the beginning of the research where we are, but we are actually are working on this already and have some first very encouraging results. And if we can change the shape of particles that we can create, then that means we can actually shape, for example, the cell uptake of these particles. So if you look at drug delivery, we can start to fine-tune much better how do we get a particle, how do we get a drug into a certain cell, for example. And that's something that we really would like to connect for the future. We're not there yet. But at the moment that we can make these particles, and again, we are making them in a flow process where we mix everything together and create our particles in a continuous way, which again works a lot better in terms of precision in comparison to the classical pathways. But mostly we can actually now start controlling the shapes of these particles. And that's some data we got at ANSTO in Sydney, where we determined the exact shape of our particles, and we can see now we can actually start tuning that. And the really interesting thing now will be to correlate this shape information with the information from the synthesis. And that's where machine learning again will become extremely interesting, because that's a connection that we do not understand. We do not have the chemical laws to describe that precisely. But machine learning will probably be able to make that connection. So we can actually finally reach that goal that many nanochemists actually have since ages, in saying we can correlate the molecular structure to a final product, to a final application, such as drug delivery. But what we need for that is we need automation, we need a lot of data, because machine learning only works if we do have a lot of systematic data. So that's where this all comes together. We need these machines which are able to mass produce, to systematically vary conditions, that I can read out automatically what we get in order to make these correlations. And I hope that was enough as an example for you to actually see, okay, this is something that might be happening in future. I've shown it now for the polymer chemistry example. But as I mentioned earlier, actually a lot of pharmaceutical chemists, especially in the field of pharmaceutical chemistry, are also working on these things. A lot of pharmaceutical companies are working on this, on fully autonomous reactors. And I truly believe we will see a lot more of that. And the chemical space is going to change. The bottlenecks that we find in our lab nowadays is mostly programming skills. So this all means that chemists will need to start learning programming much more than they do today. We need to be more trained in electronics. We need to be more trained in circuits and understanding how all these things work. And it's going to be important to do that. Because, yeah, as I say, in 10 years, we will see a lot more of these systems in all different fields of research. And with that, I want to thank my group, which is actually split over 3 continents at the moment. I still have from my past appointment in Belgium. Still actually 3 students here, Kirsten, Louis, and Greg are left. They still have to graduate with a PhD. Some students via our Monash IITB connection in Mumbai. And actually here on this side, you see the names of the group we are working with here at Monash. And with that, I thank you for your attention.
Thanks very much, Tanya. And I'm sure there's a virtual clap in the background there somewhere. We can't hear our participants today, but we're certainly getting some questions coming through. Now, you're happy to answer some questions?
Of course I am.
Fantastic. So I might kick off with what might actually seem a bit of an obvious question given what you've been talking about, and that is, do you think that automation and machine learning will make chemists unemployed in the future?
Well, that's an interesting question. Actually, I jumped over that in my presentation. There was a very interesting article published last year in the Chemical Engineering News from the American Chemical Society, which was raising that question. And I do not think that's going to be the case. I think chemists will have to be differently trained, but they won't be unemployed, because creativity is still something which is inherently human. And as I would say, chemists will have more time to actually do the fun part of chemistry and will need to do less of the boring bits. But it will require a certain retraining. Again, taking car manufacturing or cars as an example, if you go back 30, 40 years, a car mechanic was a mechanic. So what they needed to know was mechanics. Today, a good car mechanic needs to know a lot about computers, electronics. So actually mechanics is just one part of the job. Actually, it's much more important to be able to look at computer chips and reading out data. So the same thing is going to happen in chemistry.
So you talk about creativity being this sort of element of humanity that is important for the process, but could a machine itself be creative?
Well, that's the interesting thing. I mean, I'm not a computer scientist, so I'm not sure how far creativity actually really goes. I hope that we will always be better than computers in that, but for sure computers will also get the creativity part more and more in the future.
Fantastic. So next question is, have you had a chance to access the flow chemistry lab over at CSIRO? And I'm not sure, how does that compare to your system at the university?
Yeah, I got the FlowWorks at CSIRO, which is an excellent laboratory. And we do collaborate with them. I think we differ in the sense that we are, well, obviously a bit more academic in the research we are doing, but also that CSIRO is more focused really on scaling of chemical processes. So it's more like companies coming to them saying, we have this process, we need to make 10 tons of that, can you help us? And they are perfectly equipped to do that job. While our goal is more making new things.
You're on the cusp of discovery.
Yeah.
Can you tell us about some of the polymers you have made?
The biggest part what we're doing is actually blockopolymers. So as I outlined at the end, so we are now doing a lot of the research in the area of self-assembly, where we want to use these polymers now in drug delivery, because there's a lot of data out there. A lot of chemists have worked on this field in the past 30 or 40 years, really. But if you look at the data, it's always very something here, something there. It's not systematic at all, and that's, I think, why we don't have a deeper understanding of the systems. And as I was mentioning, I think that's really where automation can come in really handy in making this data available in a systematic fashion and actually understanding what we're doing.
Cool. Next question. Interesting question. Flow chemistry and its automation appears to have the potential to really change traditional synthetic chemistry and make it accessible to non-chemists. Could this sort of technology be misused, such as in clandestine drug labs? You know, what moral obligations do scientists need to have to make sure this sort of technology is being used for good, I suppose?
That's a really good question. Actually, I've never had that question before. I normally phrase it in a positive way in saying that by making chemistry available to non-chemists, you can actually create a situation where my perfect example is a medical lab needing materials, and they will have difficulty finding chemists to do what they need, because very often what they need is a bit boring for us. So giving them such a machine would actually accelerate their research a lot. So I see a lot of potential there. Same as in being very flexible in production, which is very important for supply chains, and probably the pandemic has shown us, especially Australia is vulnerable to supply chain problems. We need to be more flexible, and flow chemistry can step in there. But yeah, indeed, everything you develop can be also used for something evil. I think that's a general problem that chemists face, that whatever we develop can be used for good or for bad.
Sure. Food for thought though, isn't it? Okay, let's move to a technical question now. It really shows someone was paying attention to the chemistry. How would you implement heterogeneous reactions? So for example, with a catalyst in a flow reactor?
There are different ways to do that. In my own research, we tend to avoid that because we are dealing with polymers, which are all very viscous, and that comes with its own set of problems. But you can do this via flatbed reactors where you're flowing over a catalyst, or Cyro has a really interesting technique where they actually create a turbulence in the reactor via an insert, and the insert itself is a catalyst. It's beautiful technology. So there are many different ways how you can do that. Or you have a cartridge like a column where you pump through. So it's perfectly possible to use catalysts.
Cool. And so obviously one of the hot topics of 2020 is COVID. Is this technology, is it being used for any of the sort of vaccine development, or does it have potential down the track as we get closer to large scale vaccine development? Do you see it playing a role in any way?
If you look at the classical vaccines, or also the newer mRNA vaccines that are developed now, I think that's more biotechnology. So I'm not quite sure how flow chemistry could come in there. I wouldn't say it's impossible, but I don't have the knowledge. Where it is definitely very useful is for making drugs. So for sure, next to vaccines for COVID, we will probably also be seeing drugs being developed against the disease. And that's something where flow chemistry is really handy. So actually the FDA, Food and Drug Administration in the US, has actually already issued, I think it's almost 6 or 7 years ago, that they expect all pharmaceutical production to go into flow, because it's much more efficient and much more precise, which is all something you want to have for drug production. I know, for example, a colleague of mine in South Africa, he's working on AIDS medication, specifically in South Africa, because it's a big issue there, obviously, but also because flow chemistry is something you can bring to the customer. So instead of making a drug in one part and then having to ship it over the whole world, you can actually put your reactor on a ute. Yep. And drive to where you need it and make it there.
Fantastic. I've just got enough time for one more question, and I actually quite like this question, and it relates in some ways to how in our science degree we've introduced a new subject for students, which is coding for science students, which we've seen as is clearly, as you mentioned, an important skill, I think, probably for not just chemists but all scientists and science students going forward. The question specifically is, what other skills other than programming do you think chemists or scientists in general need in the future to keep up with the changes in technology?
I think coding is certainly one of the most important things, and a basic understanding in how machine learning actually works. So a basic understanding of algorithms, which is something probably everybody in our society would probably benefit from having more knowledge in, because it's affecting us in so many different ways, and even in places where we don't expect them. But I think generally what chemists also probably will need is a bit more affinity to technology. Most chemists actually have that probably, but yeah, being really wanting to put something together and not being shy of connecting different parts and seeing what's happening. Maybe get a bit back, actually, because my personal feeling is that the generation of chemists 20, 30 years ago knew a lot more about these things than students do today. Today, a lot of technology we have has become a magic black box, like a spectrometer. It's like you press a button, you get a spectrum. And what actually happens in the background, I think that we need to teach that more again.
Fantastic, and I completely agree with that. You know, it wasn't until I was well into my PhD and postdoc that I was given the opportunity to make things rather than just using pre-existing instruments and glassware, and it was both scary but a lot of fun at the same time. So, so thanks for sharing some of your examples of your home-built equipment, so to speak. So all that's left is for us to wrap up, and in particular for me to thank you, Tanya, for sharing your knowledge about this emerging space for chemistry.
My pleasure.
And thanks to everyone for tuning in today. So thanks for joining Monash Science. We hope to see you in the future in person. So we're running more and more of these alumni events. We've started doing these sorts of things in the last few years. We've done it virtually in 2020, but you can be sure that there'll be in-person events coming up in the future. This session was also recorded, so if you want to go back and watch it, or if you want to recommend it to any of your colleagues or other alum who couldn't make it today, feel free to let them know. And we'll be shooting out a short survey if people don't mind having a quick go at that, just to inform us and tell us what the next sessions should all be about. Okay, thanks to everyone. Thanks again, Tanya, and we'll see you at the next one.
Okay, thank you. Bye.